All right. Welcome on in, everybody. Looks like everything's right. Okay. So, um, welcome. So, here's where we're at. We're moving along, moving through chapters. We're going to keep moving along. We have a couple of short chapters coming up after we finish this one that we're on, and then some that we want to slow down and really take our time with, because a couple of really important ideas are coming up towards the end, and they are things you definitely are going to want to include in your project, right? If you didn't talk about some of that stuff at the end, I would definitely call the project incomplete. So a couple things I want to mention. Oh, two announcements. So one is the school has come to its senses and realized that those of us teaching 100% online, it probably makes more sense if 100% of our office hours can be online, right? So we took till the middle of the semester to sort of get that figured out. So, because the truth is students who are taking online classes tend to want online office hours, because the whole point of an online class is that you don't have to go to school. So having to go to school just for office hours is a pain, and the truth is people don't show up, right? On Mondays, where I have those 3 office hours, I think I've had like 4 or 5 visitors all semester on Mondays, whereas I'm getting that, regularly students are dropping into my Zoom office hours that happen on Tuesday and Thursday. So just a reminder, I have office hours, so please come ask me questions, right? You're better off asking me questions on your project. If you have questions, ask me before you do the project, rather than going, well, I wasn't really sure how to do this part, and then getting a bad grade on it. Work together with your groups, talk it out, and then, if your group needs to come talk to me, and we'll figure it out, and I'll point some things out to you and leave some things up to your group to kind of figure out, and then you should end up with a better overall situation. But the main announcement is that my Monday office hours will now happen on Zoom. So if it's a convenient time for you Monday afternoon to come ask me questions, 11 to 2 Mondays, hop into Zoom during those times and come ask me questions. I'm available to talk to you about whatever concerns you have about the class, whether it's your grade, whether you're nervous about the project, whether you don't understand a certain topic, you have problems with the homework, right? All of those reasons are people that come see me in office hours, and I'll do what I can to help you and sort of give you some advice and some information and try to clear things up for you, and then you can move ahead and keep being successful in the course, right? So yeah, feel free to take advantage of that. I think that's much better. I go from having 2 online office hours now to 5, which I think is an improvement for students who are taking online classes, right? So keep that in mind. And then what was the other thing I was going to say? Oh, so I graded a couple of the project discussions that you're doing. A couple of those have been graded now. These ones at the ends of the chapters, correlation and project visuals, I think is what I did yesterday. So I just want to explain a little bit about how I'm grading those, because I don't want anyone to get like a false sense of security or misread what that grade means when I'm giving you a grade on these assignments right here. I want you to understand what it means so that you can make sure that your project that you turn in is still as good as it can be, because that I don't know what it is, maybe 2/3 of the actual project grade, not quite 2/3, come from the actual project, and about 1/3 of the points come from these discussions that we're having along the way, the project visuals and correlation that you guys turned in a few days ago, and I graded them yesterday. So I just want to tell you my approach, my strategy when I'm grading these discussions, because it's different than how I grade the final project, okay? So these discussions along the way are meant to serve a couple of purposes. One, it's to get you in there and get you using the material, because some students, if I didn't do this, would learn here in chapter 3 what a histogram was, and then they wouldn't make one until week 17 when they're trying to put their project together. That's not really a good way to learn things. You're supposed to be doing the things as you learn them. So one of the reasons for these discussions is to get you working on the material throughout the semester and not waiting till the last minute, right? Procrastination is one of the biggest enemies of really humans in general, but also just, and being successful. The number one thing, research has been done on this, the number one thing that keeps people from being successful is this procrastination. They negotiate with themselves that they can just wait to do something later. And then two things happen. One, they stress themselves out trying to do it at the last minute. But also the reality is when you're doing work at the last minute, it's just not good. It just isn't. Like you should, when you're negotiating with yourself about procrastination, just face that fact and say, well, if I do it later, it's not going to be very good. Because as a professor, I can tell you that the people who do stuff last minute, it just isn't as good, right? And in life, this holds you back. It's going to hold you back at a job. If you're doing the stuff you're supposed to do at the last minute, it just isn't going to be very good, and you're going to get passed up for promotions and stuff like that. So it's to get you using the material, getting you used to StatCrunch, getting in there and understanding how it works, understanding how to post stuff up into Canvas, and all of those things. So if you take an honest effort in these discussions, like if I can look at it and go, okay, this person went in and they made some legitimate graphs, and they did some different stuff, I'm going to give you full credit, okay? Because you're just learning how to do this in, whatever week we're in. You were brand new at making these visuals. So I'm not expecting that your visuals are going to be 100% perfect at this point, at this week, October 13th. One of the things you should do is learn what other people are doing, right? That's one of the reasons it's in a discussion board, because I could just have it as an assignment where you all submit your stuff and I just go through and grade them all. The whole reason it's in a discussion is so that you can go through and you can look at what other people did. It's going to take a few seconds to load all these pictures because this page is full of pictures. But you can go in and you can look at what other people did and you can learn from it. You can go, oh, I like this one thing that they did. I'm going to try that. Or, I liked how their histogram is. Or you look at someone's stuff and you go, I kind of don't like how they did that, and here's the reason I don't like it, and I'm realizing I'm doing the same thing. And then you can go and fix it. So what you should be doing is looking at other people's stuff and realizing, ooh, can I do better? Is theirs better than mine? Is mine better than theirs? And to either one of those questions, ask the question why, and then you're learning what makes a better graph, which means the one when you go back and sort of make everything a little nicer at the end of the semester, hopefully you'll make them better because you've learned from looking at other people's stuff. You may come in here and realize, oh, these people made a bunch of graphs. That's way better than what I did. I made like one graph for my whole project. This person made like 12. Maybe I should make some more than just one, right? Different stuff like that. Or, you're figuring out, oh, look, this has different colors in it. Oh, that's a good idea. Kind of like how that's done. Or, you might see one like this, or, oops, can't see it on the screen, but, just try to learn from what other people are doing. Take a look at it. That's the whole reason it's in a discussion board. And, you don't have to, it's not like there's no shame or anything. You look at someone's graph and you're like, oh, I don't really like how they did that. There's no shame in that. There's, you just move on to the next one, find one you like. But the point is to be learning along the way, because really, if you turn in the graphs that you made, that you turned in whatever it was 4 or 5 days ago, if you turn those in, then at the end for your actual project, they're probably going to be missing a couple things. But if you look around and learn from what other people have done and go, oh, you know what, there's a couple changes I can make to my stuff, you might be able to make it a little bit better graph. Right? So that's the idea. It's not just post this, you get some points, and go, okay, I'm all ready for my A at the end of the semester. Because the truth is, some of you got full credit on the project visuals. I'm not talking about anyone, and I'm not pointing out the ones that I looked at specifically in there. I'm just saying most of you who legitimately did the assignment got full credit for your for your project visuals. That doesn't mean your project visuals are ready to go into your project, is what I'm trying to get at. So just because you got full credit here, that doesn't mean, yep, A work. That means good. You're getting in there. You're using the the tools. You're using StatCrunch. You're figuring out how to save a file and to save it to something else. You're playing around with it. But that's not the end of the story. The story should continue with you looking at other people's stuff, learning from what they did, and then deciding how you can make yours better. That's what we're getting at. So some of you got full credit for this project visuals, but if you post those same visuals in your final project, you might actually get marked down because, oh, I forgot to put in labeling, or I just really did one graph for my whole entire project, or like, whatever. If you think about it, it's a visual medium that you're making a video, right? People want something to look at. Just like if you're on the YouTube stream, I'm showing you stuff the whole time, right? That's why if you look right now, no one's on the Zoom stream, everyone's on the YouTube stream. Why are they on the YouTube stream? Because I'm showing you stuff, right? It's not just looking at my face the whole time. I'm showing you things for you to look at. That's a lesson that you probably want to use in your video, because if you're giving us visuals the whole time to look at, then I'm getting more information, right? Now, that doesn't mean that's all you should talk about is project visuals, but you might put up a visual, talk about it, and then you talk about something related to that. Then you talk about your hypothesis test. You talk about your confidence interval, and you have maybe some different visuals up there, right? You're going to have to decide how you want to do that. So just keep that in mind. Getting full credit on this doesn't mean that your visuals are A+ work. It means good job. You kind of went through. You did the assignment. You're going in the right direction, but you still want to be polishing that over the remainder of the semester, right? It's like, when you have a baby and it's taking its first steps, you're not going to sit there and critique its first steps and be like, you look kind of wobbly, baby. Come on, just put one foot in front of the other and walk more confidently. Why are you like tottering all over the place? Right? It's like when you first learn how to do something, you're kind of shaky at it. And then over time, a few weeks later, then that baby's walking a little better, right? It's the same thing here. You guys are just learning how to do this kind of stuff, so I'm not expecting it to be perfect. But by the end of this semester, you should be able to make a really bulletproof visual or number of visuals that accompany your project, okay? So I just want everyone to understand what those grades look like for now. Same with the correlation. It doesn't mean everything you did is perfect. It just means good. You went in there. You did an honest attempt at the assignment. I want to give you some points, right? And then that helps when you go into the project because you already have quite a few points if you've been doing these along the way. So that gives you a little bit of cushion when you start to lose some points on the actual project. It sort of helps a little bit. Okay? So if there's any questions about that, come see me in the office hours, or even ask now. If you have a question, throw it into chat or whatever, and we can talk about it. But if you have questions about the project, come see me. Come talk to me about it, right? And we'll get that figured out, okay? Okay, so where are we today? I think we're doing, or I know we're doing, counting techniques. So we're looking at counting techniques. And then we'll kind of look, we've got not too far away. You've got a bunch of stuff due October 26th. And then November 2nd, not that far away, you've got another set of stuff. So we'll sort of finish up Chapter 5 this week. Next week, we'll get into Chapter 6. And we'll kind of move on. We'll move forward from there. Okay? And as always, if there's any questions, let me know. So counting techniques. Counting techniques are one of those things that sort of everyone thinks they know how to do. But you don't necessarily know how to do anything but the most basic counting technique, right? You tell people, okay, today we're learning about counting. They're like, oh, no, I got this under control. I've been counting since I was 4, right? That's fine. But most people have mastered, at this point, hopefully, mastered the basic counting of just looking at something and going 1, 2, 3, 4, 5. Like, that's not what we're talking about. That's, like I say, 4 and 5-year-olds kind of have that figured out. So what we're talking about today is counting things that are hard to count, things that you can't just count off one at a time, going 1, 2, 3, 4, 5, 6, and doing it that way. So, like, what are we talking about then? Well, actually, let's see. I was going to make one comment, and then I think I distracted myself here. Let's see. No, that's right. Okay, that's what I was going to say. So 2 different things that we're going to count fall into two different categories. And at first, you're probably going to go, I don't care. Who cares about counting things like this? What's the difference? But then you'll start to see there's actually a lot of things that these formulas allow us to count that are real world situations. Sometimes we come up with kind of silly examples of counting, but that's really because we're trying to give you simple problems, right? We're not trying to start off with a problem that you would actually run across on a job, because that's probably very complicated. So we're coming up with artificially simple problems that you never will actually do in real life, but it gives you some experience using those formulas so that when you actually run across a real world situation where you have to use that formula, you know how to do it. Right? That's a difficulty we run across in mathematics a lot of times, is people are like, well, I hate word problems. I'm never going to have to do a problem like this one word problem. Right, because we've made it so simple that it's kind of ridiculous, but it's in order to allow you to use those formulas and those techniques so that you can use them elsewhere later on. So the first thing we need to do is wrap our brain around two different types of combinations, right? And I'm using the word combinations because that's like in the broad sense. And then we have capital C combinations, which I'll tell you in just a second. So why are we doing this? Why are we counting anything? Remember, when it comes to probabilities, that denominator in the numerator and the denominator are counts, right? The numerator, you're counting the number of ways the thing you care about can occur, and the denominator is the total number of ways that things can occur, right? So in other words, you have to count things. You have to count the sample size. You have to count the number of outcomes that match what you're thinking of in order to come up with probabilities. So inside of that, there's this, like, when I was doing my graduate work, I had a large part of my graduate work involved combinatorics. Combinatorics, this is like the very basics, earliest steps of combinatorics, where you start talking about how you count these things, permutations, combinations, stuff like that. Permutations and combinations are groups of things. So what kind of groups are they? Well, permutations of items are arrangements in which different sequences of the same item are counted separately. For example, if we have a set of the letters ABC, the arrangements ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as different permutations, right? So when we say permutations, we mean that we have these written in a different order and we count them separately. You'll hear this a lot when people are talking about combinations and permutations. You'll hear people say the term order matters. What they're saying is, if the order changes, does it count as a different thing? Well, with permutations, the answer is yes. With combinations, well, I'll read it. Combinations of items are arrangements in which different sequences of the same items are not counted separately. For example, with the letters ABC, the arrangements ABC, ACB, BAC, BCA, CAB, and CBA are all considered the same combination, right? And at first, it's very easy for a person to look at this and go, why would I ever care? When am I ever going to be counting things where the order, if you put them in a different order, it counts as a different thing, or you put them in a different order and it doesn't count as a different thing? What is the difference? There's actually a lot of ways that these come up, and then a lot of people, it's like anything in mathematics. A lot of times people just get to a point where they're like, I don't know how to do that, and they give up and sort of leave. And then they go, well, who needs math anyways? But those same people are running into areas that they can't do stuff, and then they give up and walk away. If you understand this, there's quite a few areas where you can use this stuff on a regular basis. So let me just start with the typical, right? And so some of you may use this kind of stuff in the future, some of you may not, but this is like the stereotypical first problem that you do when you look at combinations and permutations, and it helps you remember the definition. So that's why I'm kind of talking about these a little bit, because if you can't remember the difference between permutations and combinations, this whole section is going to be very, very difficult. So you want to make sure you're comfortable with those definitions. So permutations. Let's say that we took our class, and inside of our class, we said we want to figure out a president, a vice president, and a secretary position. Maybe treasurer. Let's make it a treasury position. President, vice president, treasury. Okay, so we look around the room, right? All of us, if we're on Zoom or in person or whatever, we look around and we think, how many different ways are there to do that, right? So, for instance, it could be that we were going to pick a position randomly. We were going to pick president, vice president, and treasurer randomly, and you're sitting there like, I don't want to be picked. That's extra work. I don't want to do it. I don't really want to be a part of any of that. So you're trying to figure out in your head, what's the probability that I'm going to end up on this committee, or that I'm going to end up as vice president, or something, you know, all these different variations of the question that can be asked. Well, if you're going to calculate probabilities, you need to know how many different ways that thing can occur. Remember our definition for probability, the number of ways it can occur over the total possible number, the number of ways the thing you're looking for can occur over the total number of ways that the things can occur. Well, you're going to have to count those. So how would we get there? How would we count the number of ways from our class that we could pick a president, a vice president, and a treasurer? We haven't learned it yet, but we'll get to that in a few minutes. And then what about if we just said, you know, there's this one project that we'd like people to investigate, but we don't need the whole class to do it. Maybe we just need a subgroup of people to do it. Why don't we pick a group of 3 people in a subgroup and assign them to work on this project? Okay, and we do that. How many different ways are there to do that? How many different ways are there to pick a committee, a 3-person committee from the class, versus how many ways are there to pick a president, vice president, and treasurer? And are those the same number, right? If we go through the class and we pick the number of ways to pick a president, vice president, and treasurer, is that the same as the number of ways to pick a 3-person subcommittee? And the answer is no. Permutations are the way that we would pick president, vice president, treasurer. That would be all the ways that we can make 3-person permutations out of the entire class. It's going to be a very, very big number. That's the other reason we can't count these by hand, because you might think, what if I just made a big list of all the combinations or all the permutations and then I counted them? Most of these problems get big very, very quickly, to the point where even some basic problems, if you spent the whole rest of your life making a big list and counting, you wouldn't get the whole list. That's how big some of these numbers get very quickly. Like the number of ways to pick president, vice president, and treasurer from the people in this class, you might be able to get it in your lifetime, but it would take decades for you to finish making that kind of list, because it would be absolutely exhaustive, and probably you'd make mistakes. Well, it's almost guaranteed you'd make mistakes along the way. So that's the 2 big problems. Some of these problems are too big to do by hand, so we have to use formulas, and then some of them are just, you can't count them in order: 1, 2, 3, 4, 5, 6, 7. So and the number of ways that we could pick a subcommittee for the class, that's combinations. Okay, so this book kind of gives you a way to remember them. Permutations is position, combinations is committee. So the P match permutations position. So when we talk about position, president, vice president, treasurer, those are positions that you would hold in some kind of administration. So permutations goes with position. Combinations goes with committee. If we were just picking a group of 3 people to form a committee and everyone on the committee is equal, there's no like, well, I'm the president, so I'm in charge. Well, I'm the treasurer, so I handle the money. There's none of that. It's just there's a committee with 3 people on it. They all are equal members of the committee. That's combinations. Because let's say we're picking for permutations. If I pick you first, you're president. If I pick you second, you're vice president. If I pick you third, you're treasurer. That's different than if I pick in a different order. If I pick those same 3 people in a different order, they now have different positions. But for the committee where you're all equal, if I pick you first, the person next to you second, the person next to them third, that's the same way as if I pick that person on the right, then the person in the middle, then the person on the left, right? You're going to get the same committee either way. So that's what we really have to do when we count these different when we're counting things. So that should be your first question when you're doing these types of problems. Is this a permutation problem or is this a combination problem? Because you have different formulas, and the formulas are fairly straightforward, but you'll want to you want to identify which is which. Otherwise, you're going to end up using the wrong formula along the way, right? And here's an example for statistics why they start using like counting, like weird counting ends up getting used. So they have a discussion here of group testing. Group testing is a technique that's used in statistics when maybe you have a whole lot of tests to do, right? And they actually talked about doing this with early on. There was some discussion of doing this kind of stuff with coronavirus testing before, like right now, there's tons of tests. You can just go get a test. But remember in the early days when there weren't enough tests and they were saying like, all the coronavirus counts were super low because like in New York City, they're like, we're not wasting tests on dead people. We know this. We know these 20 people over here died of coronavirus, but we're not going to use tests on dead people because we have live people who need them. Right? Now everyone can sort of just go get tested easily, but when they were first developing the tests, it was a problem. So what they can do here is called group testing. So imagine like they first started this, it says, when they were testing Army during World War II, Army individuals were getting tested for syphilis because syphilis is one of those things you don't want it to go on for years and years. You can do irreparable damage to yourself. So what they were doing was testing people. Well, that's one test per person. And if you start running low on tests, all of a sudden you have huge amounts of people not getting tested. So what do? Well, you could put them in groups of 5. So you take blood samples from 5 people, and then you take a little bit of that blood and put it in a new vial from all 5 people. So now you have a sample that has the blood from 5 different people, and you test that. So that only takes one test, right? But if the test comes up negative, then you've just cleared 5 people with one test. So see how this isn't the normal kind of counting where you go 1, 2, 3, 4, 5. We just cleared 5 people with one test. That means that there's an interesting kind of counting going on here, right? And then if the sample does come up, yep, someone in this group has syphilis, then they would go back and they would test all 5 people in that group. They would test all 5 of the samples, and then they would see who had it. But in that case, let's say we had 10 people, and one person has syphilis, right? So you could just test each person individually. That's 10 tests. But if you put them in 2 groups of 5, you test the first group and say, nope, they're all clear. That's one test to clear 5 people. You test the second group and say, nope, this sample came up positive for syphilis, and then you test all 5 people. That's a total of 7 tests, because you use 6 tests on the second group and 1 test on the first group. That just means you use 7 tests instead of 10, right? So you just save 3 tests. Now that might seem like it's not very much, but once you start getting into, say, testing 100 people in groups of 5, you probably will get away with using like 30 tests instead of 100 tests, right? So all of a sudden, not only does it become more cost effective, but also if you're short on tests, it's a good way to use them. But it's a different type of counting and keeping track of things, okay? All right, some things you need to know. Guess I'm going to need to move this. Oops. Let me do this. Will this work better? Only a little. Sorry, I got to move my windows around. They're overlapping, and I'm trying to make sure we can read this definition here. There, that should be okay. Kind of distracting the way I have it, but this will work. Okay, notation and some formulas that you're going to use. So the factorial symbol is an exclamation mark. In mathematics, when you see an exclamation mark, that doesn't mean what it means when you're reading a novel, right? It doesn't mean that this person is yelling that. What the factorial symbol means in mathematics is that you take the number next to the exclamation mark and you multiply it by every integer, every successive integer decreasing by 1 until you get to 1. So they have an example here. 4 factorial is 4 times 3 times 2 times 1 equal to 24. 5 factorial is 5 times 4 times 3 times 2 times 1, right? 7 factorial, 7 times 6 times 5 times 4 times 3 times 1. And then you figure out, what it is. You can just do this on a calculator, but some scientific calculators are going to have a factorial button on them. You can go through and do those. One thing that throws people off is 0 factorial. You would kind of think, oh, well, 0 factorial should be 0, right? It's not. It's 1. 0 factorial is 1. And this kind of bothers some people at first, but if you start learning more about combinations and permutations, it actually makes a lot of sense that 0 factorial should be defined to be 1. Because when we start putting things together, this is what? Let's say you have 4 different, we'll learn this. The factorial symbol, when would we use this factorial? Let's say you had 4 different objects in front of you, right? You've got your keys, your phone, your wallet, and some change, right? Or let's say a quarter. So would I say your phone, your keys, your wallet, and a quarter? These were all in your pocket. You put them on the table in front of you. What is the number of ways that you can arrange those items in front of you? And the answer is 4 factorial, because you have 4 choices for the first item, right? You can either choose your wallet, your keys, your phone, or the quarter. Okay, so you put that on the table in front of you. Okay, how many options do you have to pick the next thing in line? Well, you've already used, what did I say? Did I say the phone or the wallet? I forget which one I said, but let's say you used your phone already. Okay, you now only have 3 options for the next item because you've already used the phone. The phone is used. You don't have 2 phones. You can't put the phone down next to the phone. It's just one phone. So now that you put your phone down, you had 4 options for the first space. Now to move to the second space, you have 3. You can either choose your wallet, your keys, or the quarter. So you put that down. How many options do you have for the next place? Well, there's only 2 items left, the keys and the quarter. So you put your keys down. How many options for the last place? And you could argue this isn't even really an option, just the quarter. All right, so you put that down. So the number of ways that you can arrange those is 4 times 3 times 2 times 1, or 24. So the factorial, the way it gets used a lot of times, it's the number of ways that you can arrange n items in front of you. So if you have 7 factorial, that's the number of ways you can arrange 7 items in front of you. 4 factorial, the number of ways you can arrange 4 items in front of you. So 0 factorial should be the number of ways that you can arrange 0 items in front of you. How many ways can you arrange 0 items in front of you? 1. You don't have any items in front of you. That's how you arrange them, right? So it actually makes a lot of sense when we start talking about combinations that 0 factorial should be equal to 1. But you have to remember that because sometimes this comes up in formulas and people make it as 0, and then then all their work is like messed up at that point. So please remember, 0 factorial is 1, okay? Okay, so here's some counting rules. Fundamental counting rule. M times n equals the number of ways 2 events can occur, given that the first event can occur m ways and the second event can occur n ways. This rule extends easily to situations with more than 2 events. So you can take this idea and just extend it to 3 events or 4 events or 5 events, right? So their example, for a 2-character code consisting of a letter followed by a digit, the number of possible codes is 26 times 10 equals 260. So let's say we were going to give everyone in the class, this is kind of like on vending machines, they have like a number. A lot of times there's a letter and then a number. So you pick a letter, you pick a number, and they don't usually have all of them. But you can see how, yes, there are actually things in life that get assigned a letter and then a number, right? Why do they do that? Why don't they just have everything be a number? Well, if you just had it be a number, how many 2-digit numbers are there? Right? Assuming you don't use 00 and you wouldn't use like 05, something like that. How many are there? There should be 99 then, right? Well, there would be 90 from 10. No, there would be 89 from 10 to 99. Those are all the 2-digit numbers. If you wanted to include the 0 first, depending on what you were doing, you might. Then you would get 99 of them because you'd have 00, 01, 02, 03, all the way up to 99. But 99 is less than 260. So if we decide to do a combination where it's a letter and then a number, well, you have 26 ways of picking the letter, 10 ways of picking the digit, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Multiply those together, you get 260 combinations. So what that allows us to do is kind of, if you're ever going into computer science, it's like half your life is figuring out this kind of counting and how can I be efficient with things and how can I make more possibilities for myself. We'll talk about license plate examples coming up. This is how you count the number of license plates of a certain type that can be created, which is actually a much more important question than you might think it is. So see how we got 260 instead of 90 out of that. So that fundamental counting rule is important, and we kind of just used it up here. That's why the factorial comes into play, is because you're basically using the multiplication rule, but in a situation where the number of options is decreasing by 1 each time, because you keep using an option each time you do it. Okay, here's our factorial rule. N factorial equals the number of different permutations. See where it says order counts? I told you you're going to start hearing the phrase order matters or order doesn't matter. Here they're saying order counts, order doesn't count. So n factorial is the number of different permutations of n different items when all n of them are selected. That's what we just kind of worked through this a minute ago when we did the phone, wallet, keys, quarter example. This is exactly what we did. We used the factorial rule, right? This rule reflects the fact that the first item may be selected n different ways. The second item you have one less way because you already used up one of your choices. And then the third spot, you're missing 2 choices because you've already made 2 of those choices. And it goes down by 1 each time until you finish everything. So their example here, the number of ways to arrange the 5 letters A, B, C, D, E is 5 factorial, giving you 120, right? Like I say, you have some calculators that will have a factorial button, some that you just have to do it by hand. So let me show you. Let's see. So let's say we want to do 5 factorial. Be 5 times 4 times 3 times 2 times 1. And you kind of don't really have to do the times 1. But so you see how we get 120? So you just do it the long way. Now this doesn't work when you want to do 100 factorial, but you actually run into problems if you try to do 100 factorial anyways. I don't think... Oh, in fact, there is a factorial button here. So this is just the calculator that's on Windows. So anyone using Windows, you have this. Mac also. Mac has a graphing utility, and I believe they have a scientific calculator in there, although I don't usually use it. But I think there's one in there too. And you can certainly find stuff online that'll calculate these factorials. But if I do 5 factorial, see how it gives us that 120 again? So it's just kind of a shortcut, so you don't have to do all the multiplications. It does it for us. It says, oh, I know you wanted to do 5 times 4 times 3 times 2 times 1, but that's a little tedious. I'm going to do them all for you, and we get the 120. Okay, so look for some kind of symbol. One thing that's annoying as a math person is that every calculator is programmed and laid out a little bit differently. So you learn one calculator really well, and then you go to look at another calculator, and it's like it was written by an alien race or something, like where you can't even, like it was written on another planet, where you're like, I can't make sense of this new calculator. I'm used to my old one. And it takes a lot of time because they arrange everything differently. They use different symbols, and so it might take you a few minutes to find the factorial on whatever calculator you're using, but it's worth it once you find it for this section. Okay, so that's that factorial rule. All right, now how do we find permutations when all of the items are different? So the number of different permutations, so the order counts when n different items are available, but only r of them are to be selected without replacement. That was a lot of information in that sentence, and they've introduced a new idea that we need to be aware of, and that is with replacement or without replacement. We kind of talked about this. I talked about this a little bit last time. If I go around the room and have you pick a card from a deck of cards, and I say, okay, pick a card. If you keep that card and then I move on to the next person, that's without replacement. But if you think about it, if you pulled the ace of diamonds, that next person I go to, they can't pull the ace of diamonds, can they? Because you're holding it. So that means that all the probabilities and the number of combinations for that deck of card has now changed because you've changed the deck. You've pulled out the ace of diamonds. It's not in there anymore. All the math is different now for that next person who's going to pull a card. That's called without replacement. If I come to you and say, pull a card, you pull the ace of diamonds, look at it, and I say, okay, put it back, and you put it back in, and I go to the next person, then the probability and the combinations and permutations for that next person is the same as it was for you because they're dealing with the same deck because you looked at your card, but then you put your card back. So that's what we mean when we say without replacement, is once you use an item, it can't get used again. But if we say with replacement, that means that the item was used, but it can still be used again. So you have to kind of look closely. That can throw things off. So what are we looking at? The number of different permutations when n items are available. Oops, I'm looking at the wrong. Sorry, I started reading the wrong one. When n different items are available, but only r of them are selected. Okay, so the example I did a minute ago, we had 4 items, and we picked 4 items, right? We said, let's arrange all 4 items. Phone, wallet, keys, quarter. And we arranged them. And then we counted out that, there's actually, 24 different ways of making that arrangement? Well, what if we had 4 items, and I said, just arrange 2 of them? Okay, so just, you could go, okay, well, there's phone, wallet, phone, keys, phone, quarter. Okay, wallet, wallet, phone, wallet, keys, wallet, quarter. Okay, keys, phone, keys, wallet, keys, quarter. And you're going through all those, but you're only picking 2 at a time. That's a different problem than if we have 4 of them and we pick all 4 of them, right? Now we're only picking part of them. That's where this formula comes in. I know it's a bunch of different formulas, but really take your time when you're reading these problems and just think about like which of these scenarios matches the problem that I'm doing, and then use that formula. Okay, so this would say maybe we take, we'll just use the example we used. We have 4 items, phone, wallet, keys, quarter, and I want to pick 3 of those, say 2 of those items. Then what we would do is we would have it be, it would be 5P2. Okay, and then you would use this formula right here. So your N is 5, and your R, you're picking 2 at a time, so you would put that in here. Okay, and then you would simplify all this. This looks complicated, but just remember your order of operations. You do what's in the parentheses before you do the factorial. So let's look at what it would be for the, or is my calculator? Okay, so let's see. For our problem, we said what? 4 factorial was 24. Okay, so 24 different ways of arranging 4 items. So that's my numerator here. My denominator is going to be what? 4 minus 2 in parentheses, so that's 2 factorial. So 2 factorials, you can do that one in your head. That's just 2. So 24 divided by 2 is 12. There's 12 ways that I can take the 4 items, phone, wallet, keys, quarter, and pick and arrange 2 of them. Arrange them 2 at a time. There's 12 different ways to do that. Okay? So this looks kind of intimidating, and there's this new weird notation, but don't overthink it. And remember, when you watch the videos, they're going to explain this stuff a little bit more. I'm just giving you the overview here. Permutation rules when some items are identical to others. So a lot of times you see these as marble problems or sock problems. Those are super popular. Socks and marbles, because everyone knows what a marble is. Everyone knows what a sock is. And, and then everyone has a different way of organizing their socks. Some people intentionally wear different colored socks. My approach is just buy a ton of the same socks. And every sock's the same, so I don't have to match them. Every sock I have is like a black sock, right? Because I don't really like doing this kind of math when I get up in the morning. But you've got permutations rule when some items are, let's see, make sure I'm not skipping. Yeah, when some items are identical to others. So you might have a problem where there's a bag of marbles, and you have 5 black marbles, 3 red marbles, and 7 blue marbles, and then you do a problem based on that. Well, your 7 blue marbles are all the same. Your 5 black marbles are all the same, right? So you have some identical items to others. So the number of different permutations here, when ed items are available and n are selected without replacement, right? So you pull a blue marble out. Now you only have 6 blue marbles left. That changes the calculations. Now you pull out a red marble. Okay, that changes the calculations each time, and we're getting this kind of a situation. This might seem like a silly situation, but this actually comes up as well, where it helps us count different types of a number of different things, right? And we'll get into some of those real world examples. And then for combinations, we're not going to have multiple different ways of doing it. Notice how we have 2 formulas for permutations, but not for combinations. Combinations, and this might look like the one we did a minute ago. Doesn't this look like the permutations formula? Well, notice they're pretty similar. This formula right here is pretty similar to this one, except, oh, there's this little r factorial on the end. What is that? Basically what that is, that's the piece where you're dividing by all the combinations that we're counting as the same. So, you know, like in the example that was given, we had ABC, ACB, BAC, BCA, CAB, CBA. What was that? That's 6 ways that are different permutations, but all count as the same combination. So that's basically what this formula is doing, is it's dividing out the duplicates. This little r factorial is dividing your duplicates out. So it gives you those combinations, and then all of a sudden, if you have the letters A, B, and C, those are all counted as the same thing because we've divided out all the different ways that that can occur. Okay, so you can see it's very similar to plug this in as what we did a minute ago, and you end up with 10 in this case for their problem. So if you do 5C3, you end up with 10. There's 10 different ways. So that would mean if we had a group of 10 people, say maybe there's an astronomy club at the college. I don't know if there is or not. Say there's an astronomy club. There's 10 people in the astronomy club, and those people want to put together a special field trip where they're going to go up to some observatory and have a viewing. But you don't need the whole group doing it. But they want to assign 3 people to do it. Right? How many different ways can you assign 3 people from the 10 to be in the committee? It would be 10 would be your N, C, and then 3. So 10 choose 3 is how we say that actually. The C, we call it as choose because you're choosing. From 10 people, you're choosing 3. 10 choose 3 is how you're going to hear people say that when we're doing a problem like that. Okay? Okay, so we kind of set the stage, right? And this comes in like choosing your PIN codes. This comes up. Like we'll talk about that next time. PIN codes and license plates and a lot of computer science. There's all sorts of different areas where this stuff becomes very important, right? So we'll talk about that next time. We'll start up right here on 177 next time, and we'll talk more about the counting. We're spending a couple days on this because I know this is very confusing for people. I find in general the counting is very, very confusing. People get confused and stressed out. So we're going to spend some time on it. Work on it, see what you can do with it, and then come to me with your questions. Come to office hours with questions, or just send me a screenshot of a problem you're working on, and then I can go over that one next time, right? I'll discuss it. I'll actually work you through the problem if you want to do that, okay? All right, thanks, everybody. I'm going to shut down the YouTube stream. Feel free to jump into Zoom if you want to talk to me. We actually have office hours today for an hour. So plus I always give people a chance to talk to me after class anyways. So if you want to come speak with me, now's a great time to do it. Otherwise, I'll see you in a couple days. Thanks, everybody.